most of you will go back to your hometown. I think most of the students, Japanese students here, are from the Kanto region, so they won't be going so far. So as a recent update, I think it's started to snow badly in the Japanese seaside. So for those of you going out, please take care of yourself. Winter sports accidents are very common, especially when the snow is very bad. So let's dive into our previous. So today we have Dr. Manraj as well, because I think a lot of students complaining that my class is boring, so he has to come to audit. Oh no, maybe it's because of last class. All right. So the problem with why I complain about the weather, because I have asthma, so every time the weather gets very cold, I run out of breath every time. So I think it's okay. I can carry on with this class today as long as I don't do too much thinking. Usually I don't. All right. No, I'm just joking. I never do. All right. So let's look at previous class activity. Right. I forgot what was the activity. So we started back with SARS-CoV-2 glycoprotein here. You can see on the screen. And then apparently 5 of you not submitted. All right. So I went through some of your answers, especially those early submissions. The objective was very easy, just to clone the glycoprotein, and you can do it as you like. Right, there's many ways to go about it. There's number 1, number 2, number 3, and number 4 instructions over here. So the problem, I think, my mistake was not to put the word for DNA sequencing, but let me start recording.
Recording in progress.
In instruction number 3, there's the word DNA sequence. All right. So I should have placed DNA sequencing in the objective as well. So that makes the objective very clear. So this process is very common when we do research, and we have a long sequence and we put it inside plasmid before we send them for sequencing for the reasons which would be answers for instruction number 4. So my main, when I was going through, I think about 6 or 7 early reports that were submitted, I was looking at how you, what was your approach to clone this glycoprotein. And then after that, and then your answer for number 4. That's what I did. And some of you were looking through the Takara restriction enzyme search tool, and then you're looking for different sites, and then you chose maybe the site that cuts once, that also cuts with once in PUC 19, and then you clone it, right? So that was the approach. I think that's a good attempt, but there's a problem, and I think some of you also did specify you might lose maybe like 90 base pair because you have to use that restriction enzyme site. And then, but I don't know, because during the lecture, I explained about the usage of linkers. And then we also talked about ligase, all right? So the purpose why I talk about ligase, so that you could use the ligase to add the linkers. Then you can have an additional restriction enzyme site that is originally not available in the glycoprotein. So that's one way to do it. So why we wouldn't want to lose any of the base pairs? Because we want to sequence the full gene, right? We want to full sequence. So it's no point of losing part of the gene because you have to choose restriction enzyme. But at least I think you're thinking about how to solve the problem. So that's a good indicator. And the next issue is the contrast between, I did mention, is what is the difference between directly sequencing the DNA and also putting it into a vector before you sequence. So directly sequencing, now I give you the hint before. You can see, let me draw a long sequence in the board. So I think in DNA sequencing was activity, we have processing DNA sequencing here. I think it was our third lecture, maybe, right? So what we did when we processed the sequence was, first of all, to remove the first, I think about 50 to 60 base pair, remove this part, and then we have to remove the one from the back, right? So the reason why we removed the ones at the 5' end and 3' end, because the 5' end was, the signal was very weak. The signal was very, very weak, but the one in between was better, something like that. Apologies for my background, right? So every time you sequence, because of the chemistry of the sequencing, you'll always lose this part, right? So at least the first 50, 60 base pair, depending on your sequence quality, you'll always lose this part. So if you were to choose a restriction enzyme and to cut somewhere in the middle, you are losing a part of some maybe valuable information that we want to sequence. So we don't want to do that, all right? So that's why we choose to add a sticky end linker instead, right? And this will join well with PUC 19. And you in the PUC 19, then you can choose your linker. When you have a blunt end here, it's no problem. You can add the linker, and then after that, you can join it to PUC 19. So the site in available in the SARS-CoV glycoprotein gene is not really important. It's not really relevant because we just want to do sequencing. So that was just something to throw off your, I think, attention. So you don't have to search the site. It's not relevant. PUC 19 site is relevant because from the PUC 19 site, you can choose which which linker, right? Linker that you want to use. Right. So some of you did get the answers correct, so there's no problem there. Congratulations. But some of you didn't. But I can see that you're thinking different alternative ways to solve the question. All right. I think because I taught you how to use the restriction enzyme search tool, and everybody was trying very hard to search the restriction enzyme search tool. All right. So today, our last part for DNA genetic engineering is to produce a recombinant protein, and you have the material over here. I will use the same material as well. So we, from our journey from the first lecture to the fifth lecture today, we did some basic things, which is all related because we are building upon what we have learned before. So from lecture 1, I think we designed primers. We learned how to do PCR. That's important because we need to have a lot of DNA to work with, and that also makes our work possible when we have a small amount of DNA. All right. Before that, I forgot the answer number 4. Let's go back. Let's backtrack a bit for clone the glycoprotein. The answer for number 4: what is the benefit of cloning into plasmid? So when we clone into the plasmid, we can use the sequence of the PUC 19 over here, and we can use the PUC 19 over here to sequence our insert, our DNA that we do, piece of DNA that we clone, which is for this case is spike glycoprotein gene, right? So when we use the sequence region from the PUC 19, the benefit is we don't have these weak signals over here because our weak signals will be over here. So we can remove this and we can read the whole length, maybe plus alpha extra compared to the whole gene. So this will give us the complete information of our gene. So we're losing any information. So that's benefit number one. Benefit number two, if we don't have a specific primer for our gene that we clone, or maybe we are doing something of nature of unknown. Let's say you use one set of primer and then you do your PCR, and then you have multiple bands. All right, you get multiple bands from electrophoresis. You can cut those bands and you can put it inside. You can cut literally just cut it with a cutter, melt the gel in agarose electrophoresis, and then extract the piece of DNA, add linkers, and then you can put it into a plasmid, right? But the problem is now we don't have a primer for sequencing, but it's not relevant because we are using the sequence of the PUC19, and we already have the information for that sequence. So it's I think it is M13 M13RV, and I think this one is M4 or M15 M4, something like that. There's a few versions. So these are universal primers, very much utilized by a lot of research. We do this to read unknown piece of DNA. All right. So for last year's final exam for this genetic engineering, I gave the question: if we send a probe to Mars and then we found a piece of DNA that we don't know about, how can we sequence it, right? So this is the solution, but I doubt we'll find any aliens DNA anytime soon, right? So just in case, right, in the future, if you're working in NASA and then you found a piece of unknown DNA in space, maybe you can give that a try. But of course, you need to put it in the vector, the plasmid PUC19, and then you can use M13 universal primers. You can sequence. You can also do PCR on unknown DNA. So this is a solution for working with unknown piece of DNA sequences. So that is the benefit of putting it into cloning plasmid. All right. So we use the word cloning plasmid in contrast with today's lecture, which is going to be expression plasmids, and then that's where we're going to look at different types of plasmid. So the next aim is just not to work with DNA sequences, because we now know how to make more DNA sequences by PCR, how to manipulate them by cutting them with restriction enzymes, how to use restriction enzymes. We can add new restriction enzymes at the end, at the terminals of the sequences, right, by using linkers. And then finally, we can put them in and join them with other piece of DNA using ligase enzyme, which is the process of ligation. So now I think we are quite good and comfortable working with DNA. And the next step is to mimic the central dogma process, which is to make protein from this piece of DNA. But of course, only structural genes can make proteins. So we want to make proteins out of structural genes. So for this case, when we make proteins, all right, we are not using ATCG anymore because proteins are made from amino acids. And I think you guys have memorized what are the 20 types of amino acids that's being commonly used for making proteins. So there's different groups over here. Non-polar groups, those are containing hydrophobic ones, and polar groups containing the charged ones, negatively charged R groups, and there are positively charged R groups, right? So you, I think most probably have learned this in biochemistry, all right? In SIT, we have that in second year, I think, right? So you have to memorize the structure, the names, the three-letter abbreviation, the single-letter abbreviation. So very entertaining for you guys, right? To tell you the truth, I've never memorized this when I was a student, but after working with them so long, you'll get used to it. So there are 4 levels of proteins. That is made from amino acids joined with peptide bonds. So these are different types of bonds. In DNA, we have phosphodiester bonds, right? And then after that, we have hydrogen bonds, which holds 2 strands of DNA together, right? So, but phosphodiester bonds is the ones more related to us because we're using them to cut them using restriction enzymes and then join them back using ligase, which is basically adding the phosphate group into making new phosphodiester bonds. For peptide bonds, it's slightly different because we are working with different molecules to begin with. We have here the C and covalent bond releasing water from when 2 amino acid residues are being formed. Right, so we use the word residues for amino acid for proteins rather than bases for so there are some differences there. In when we're working with DNA, we have 5' to 3'. When we're working with proteins, we have N terminal to the C terminal. So that is our direction. And then usually we'll simplify the side chains with the symbol R. So the first residue will have R1, the second residue with R2. And just like DNA, we can have complex 3D structure for proteins that involves not just the covalent bond peptide here, peptide bond, but also other weak bonds, non-covalent bonds such as hydrogen bonds. But we have another covalent, which is disulfide bonds, which is quite regular appearing in in protein structures. But apart from that, we have charge charge attractions, right? Positive, negative they call electrostatic charge interaction. All right. I'm thinking of words because I always memorize this in Japanese instead of English. But you get the idea. We have covalent bonds and we have non-covalent bonds involved in making 3D structures. So I think indirectly we have looked at different structures in the PDB data bank, and then you can see a lot of interaction, a lot of different structures over there. So 4 levels of protein structures: secondary, tertiary, quaternary structures. So apart from the primary, which is the peptide bond itself, beta sheets, and then we have tertiary structures, combination of the secondary structure, making different types of motifs. And then quaternary structures is when you have multiple subunits, right? So I'll just go through this quickly, explore different structures from protein data bank, like I mentioned just now. The 4 letter over here, like 1R7, 5XLR. So these are basically like the accession number for the gene from the gene bank. From the gene bank, we have long accession numbers. Usually, this 4-letter codes will be the unique codes for looking at different structures. So the resistin-like beta protein crystal structure. I think, why did I choose this one? There must be a story, but which I forgot. But now let's look at what is related to our topic today, which is the glycoprotein. All right. So always the best way to enjoy your experience using the protein data bank is by looking at the 3D view over here. You can click the 3D view depending on your internet. The connection might take a while to load, and depending on the structures as well. So from here, you can see there's multiple chains. All right, only one chain, but you can see from the color there's 3 chains. Okay, so this is the spike glycoprotein. All right, unfortunately, this figure doesn't show the glyco part of the glycoprotein. It's only showing, or choose the components over here. Nope. All right, you can see density, quality assessment, assembly. All right. So if you turn off, you turn on, you can see the symmetrical. So this is not really important unless you're looking into how it's packed when it's being crystallized. All right. Let's turn off that. You can export it if you're doing presentation. I think you can choose. Right. This particular model doesn't show the sugar groups involved in the glycoprotein. So just in a nutshell, what we can say from observing the structure, we have three different chains of proteins, right, forming a trimer unit over here, trimer structure. So it's the same protein, chain A, B, C is the same. And you can zoom in and look at the secondary structures like the alpha helix. And then there is the beta sheets over here, making not a large beta sheet, but there are beta sheets over here. So being a glycoprotein, I think a lot of the surface usually tend to be hydrophobic, all right? And then the inside of the protein tends to have more hydrophilic residues. But that's another story for another lecture, I guess. Let's go back, right? So you can also look at the annotation, for example, here. So the annotation will show chain A, which part of chain A is identified as which protein family, and so on. And then you can also look at sequences, because we're dealing with amino acid proteins. So the sequences will be amino acid sequences. So if you download this into FASTA, for example, then you'll get, hold on, open. No. They always have problems. We just open FASTA. So you're going to see a FASTA format of amino acid residues making up this protein. Right. So the problem is usually what I have is how to find the gene of this particular protein, and if you can't find it here, I think some will have. So sometimes when you look at the structure summary, you can find publications from the authors, and then if you go look into like this one, this is the publication. If you can go in and look at the publication, maybe you can find the accession number for the gene bank over there. Or this is 2017, but not necessarily that protein is registered 2017. You can find the specific, like an author, for example, and then after that you can look at search in the gene bank and look whether the author matches the author of data bank registry, and you can find it that way as well. So there are multiple ways of looking at it. Right. So the PDB file can be downloaded and then you can view afterwards. So these are, we're getting away from genetic engineering because we're talking about now. All right. Let's go back to. No, I lost my lecture. Right, my lecture's over here. All right. So our main aim is to express protein in E. coli for this particular case. The reason is simple, because that's what I do, and I've never expressed anything else in yeast, for example, or using different type of cells, because my expertise is in bacteria, and I've been working with E. coli for the past, I don't know, 12, 15 years, I guess, since I was in my master years. So when we produce something in coli, the protein from a different bacteria, if we assume, or maybe different viruses, different organisms, so the protein will be recombinant protein. We use the word recombinant protein. Then the tools that we need to use, if you need to keep a sequence, we can use cloning vectors like PUC19 here, or we can use and when we want to produce it as proteins, then we will use expression vectors, and then the rest are restriction enzyme, ligases, polymerase. We already covered that. Those are the tools that we've seen before. So these are basically like the previous lecture. We talked about PBR322. Is the backbone that's making up most of the plasmids that we're using today. So when we are cloning, there are several approaches that we can use. We can PCR and then cut the terminal so it matches our destination plasmid. So for this case, one, and then we'll cut the our destination plasmid, host plasmid will be EcoR1 and not one. For this one, not one as well. So because EcoR1 and not one anneal will not join to each other, so you only have the opportunity to form complementary joints with the insert, and then you will produce. And then after you add ligase enzyme, it will join these two DNA molecules together, right? So another approach is to start. You can, instead of using PCR, you can cut directly from here. And then put it into the host plasmid that you want to put, and then add ligase again. So you can produce the insert in many different ways, right? So this is two ways of doing basic ways. So now our focus is the difference of plasmid and expression plasmid. So cloning plasmids generally have high copy numbers so that you can produce a lot of copies so that you can cut them again later. So you can have as much of the DNA insert from cutting of it from cloning plasmid as much as you can get it from PCR, right? So there are advantages and disadvantages. Like you get less PCR error or polymerase error from inserts that you generate from plasmids because you are not doing it in vitro. You are doing it in vivo, right? And then cloning plasmid gives you a lot of priming sites for sequencing. So you don't have to use your own primer. You can use a universal primer like this M13RV, for example, which is upstream of the gene that you clone in multi-cloning sites. It's always upstream. So you can use the same priming site. So this is very useful when you have to sequence a lot of plasmids, right? And plasmid also includes a lot of RE sites so that it's easy for you to subclone. You can insert once, you can cut it with different RE, and then you can transfer it to different plasmid if you want, or whatever downstream application that you have. Another one, this is something very common that you've learned in, I think, biochemistry as well, blue-white selection, because it includes the gene that containing components that is useful for distinguishing, separating the plasmid with the insert and without the insert. So that will facilitate your process of cloning a lot faster. So I explained before as well in this genetic engineering, we are focusing more on the theory of the genetic engineering part rather than the hands-on part. So usually the blue-white here in SIT, we'll do this in the practical courses, right? So the students will have the opportunity to do this blue-white cloning themselves and observe how many colonies is blue, how many colonies white. I think that is done by Professor Fuse's class, right? Right. So now let's look at expression plasmids contain less RE sites. So the problem when we have less RE sites, as you know from the previous assignment, then it's getting difficult to clone because you have less options, right? And then after that, now this is more specific for making proteins. It has mechanism, the components for controlling production of proteins, the gene expression. Expression of plasmid generally has low. So this would be problem for subcloning and so on, because you need to produce a lot of cells before you can get large numbers of the plasmids. And then plasmids may include terminal tags for detection and purification, which is something very useful and something which we will look into soon. So previously we looked at PUC 18, 19, all right? You can see the large number of selection for precision enzyme sites from ECOR1 site to HIN3. So PUC 19, they inverted the site so that you have ECOR1 to HIN3. So either way, it doesn't matter. So depending on what you want to do, which one do you want to choose, right? Now we will look at different cloning vectors that I think we didn't talk about this last week. T vectors. So T vectors are very useful vectors because they include this blunt cloning sites, EcoR5. They cut this EcoR5 open so you get a linearized plasmid. And then when you do PCR, depending on your polymerase will include the overhang A, right? Overhang A over here. You can see the PCR product overhang A. And this would join nicely to the EcoR5 site that is being cleaved over here. So this is depending on some call it T cloning, some call it TA cloning because this is T and this is A. Your PCR product will have an overhang A, right? So this is different compared to last week's assignment. If you cut with restriction enzymes, you'll produce also a sticky end, but not just one base pair, but you'll produce, I think, about 3 base pair. Usually sticky ends will produce about 3 base pair, 2 base pair. So it's much more sticky compared to the overhang single base pair A that is produced by your polymerase. So if you want to do this type of cloning, first of all, you have to purchase your T cloning vector. All right. So there are different products. I used this one before from Takara, PT7 Blue. It's 2887 base pair. So if your PCR product is 1000 base pair, so you will add to this, so it becomes 3887, and you can confirm that using your normal electrophoresis, right? And then there's another one over here. I'm not so sure this one. I just take up from the internet, so you can see how at which location that your PCR product entered. And also you have to be careful with your DNA polymerase because the DA overhang is not produced by all polymerase. Tech polymerase will produce this DA overhang, but some high-end polymerase, high fidelity polymerase usually don't do. The KOD series, for example, they don't do. They produce blunt ends. And to be able to use a T vector with blunt ends, what you need to do is add linkers, right? Once you add linkers, you can do it again. So it's not much of a problem. So next we're going to look at expression vectors, right? The T vectors are for cloning, right? For cloning. These are not usually they are not for expression. Or the expression, we have different types of expression vectors, but here we're going to focus on the PAT system. Excuse me. So the PAT system, this one you can find a lot of information. I think some of you might be already using them. So to express protein, you need to have the promoter, right? The promoter, and then you need to have the terminator, right? And then for this case, we have the lag operator over here. So the difference between the typical expression promoter and terminator, these are from different kinds. This is not lag promoter, it's not lag operator, it's not lag terminator, but instead it's using T7 promoter and T7 terminator, right? So what's the difference is that promoters are the site that is being identified or recognized by polymerase. So T7 promoter is identified by T7 polymerase rather than the normal E. coli polymerase. So that's different. So T7 is from T7 fudge. It's a fudge, it's a virus. So they work very strongly or very well. High efficient compared to the normal DNA polymerase from or RNA polymerase from the a normal E. coli host, right? So this will make a very strong expression system. So it will produce a lot of RNA, and RNA will produce a lot of protein as a result. Right? The problem is we need to use T7 RNA polymerase, and not all E. coli has that. So you have to use an E. coli that has the gene to produce T7 RNA polymerase. So you can see from here, this is the genomic DNA from the E. coli. All right. Usually the E. coli with the DE3 designation, like BL21 DE3, JM109 DE3, DH5 alpha DE3. So that contains this piece of DNA that codes that encodes the RNA polymerase. So what happens is that RNA polymerase will be produced, and this will express the gene downstream from the T7 promoter. So here, so you need to have an E. coli that produces T7 RNA polymerase. And then regarding the control mechanism, we have LAG-I gene. LAG-I gene is a repressor, so this will bind to the lag operator, which also will bind to the lag operator here, because we have the lag operator here as well. And it will stop most of T7 RNA polymerase activity. So there is no expression, no protein production during that time. So to remove LAG-I, we add IPTG. All right, it's a compound that will bind to LAG-I, which will change the structure of LAG-I, so it cannot bind to lag operator. And because of that, T7 RNA will be produced, and T7 RNA will start producing RNA from your pet vector, right? So that's the idea, right? So this system is useful because usually when we want to produce protein, we want to produce a lot of protein, so that it will facilitate our research work, so for enzyme production, so that's very useful. Excuse me. All right, next, let's look at the features for pet vectors. There's a whole range of pet vectors, all right? The PET3, PET5, PET9. You can see the number here. This is the number of the pet vectors. PET31, PET32. But don't worry about numbers. We'll see examples later. And they have different application because they have different parts on them. For example, N terminal of the protein will have some tags, right? Like S tag, his tag. There's different tags over here. Our his purifier protein. I was gonna explain about his tag afterwards. And then we have to choose different types of pet vectors that has the parts we want to use, right? So TRX tags, for example, and then yeah, there's different types. For example, this is for Western blot. If you want to do Western blot, you can choose PET29, PET30, PET32, and so on. All right. Look at one example like PET32 we have over here. So we have the whole. This is a normal vector map as we've seen from last week. Different vectors. So this is much more complicated compared to our PUC 18 or 19, and this is where it becomes very interesting, right? So we have our LAG-I gene. As I explained, LAG-I is the repressor. So when you have a LAG-I gene also on the pet, now you also have the LAG-I gene in the genome. You have 2 copies of LAG-I gene, which means more LAG-I protein will be produced, which means more repressor proteins will be produced. So this will stop your protein from expressing until you put IPTG, introduce IPTG into your culture, right? So this is for control. Next, you have ampicillin resistant gene. This is for selection, so that you know which of your cell carries the plasmid. And this is the multi-cloning site. Right? The multi-cloning site contains single cut site of a specific REs, right? So you can see NCO1 equal R5, BAMH1 equal R1, SUG1, and so on, all the way up to AVA1. So these are very commonly used restriction enzymes. And then you have TRXA over here. This TRXA is a tag. You can see TRX tag over here, which basically produces thioredoxin, right? Thioredoxin to solubilize protein, to make protein more soluble. All right. So this is just an example. So let's look at zoom into the multi-cloning site area vicinity for this PET32 vector. For example, this is PET32A plus, right? But that's a general. Let's look at this one because there is a B plus version and a C plus version, and usually they just frame shift the ORF for matching different types of inserts, I guess. T7 promoter. So this is where the T7 RNA polymerase will recognize and bind for expressing for producing RNA. And then you have lag operator. So this is the location where the lag I will bind, right? And then you have the XBA1 site, and then you have the RBS site. We talked about this last week. RBS site is the ribosomal binding site. After RNA is being produced, this is where the ribosome will bind and start translation process. Then you have the TRX tag, and then you have the his tag over here. So his tag, I will explain afterwards. In between, you have a thrombin protease site, and then you have the S tag, and then you have the BGL2 site, RE site, you have the KPN1 RB site, and then you have the NCO ECOR5 pieces. Starting from here, you have all your restriction enzymes. So how we will use this is we can put our gene, all right? Let's say we choose NCO1 site, and then we can choose SAL1 site. So we cut this in between these two regions, and then we will put our insert inside. Of course, our insert have to be cut with the same RE, right? And then once we express it in E. coli, all right, the protein will start making proteins from methionine site because this will be the first ATG, right? The first start codon, so methionine will be here. So that will include TRX tag, will include his tag, will include S tag, and then will include his tag and tag as well, right? If your gene doesn't end with a stop codon, it will include the his tag at the end. So if your gene doesn't include the stop codon will be here, right? And TAA. So for E. coli, generally, I mean for universally, I think we have TAA, TAG, or TGA. Only three types of stop codon, and then we have typically we use the universal start codon, which is ATG, right? If you check the codon table, usually they write AUG because they always use the RNA language rather than the DNA language, right? So this is TA over here. But what if your gene is frame shifted because it's not complete? You can have you can use PET32B where it has a frame shifted and stop codon, which is slightly different. And then you can use C as well, where it's slightly, I think, where's stop codon? Stop codon will be very far, maybe. This is at the end over here. And then then you have the T7 terminator. Over here, you have T7 terminator primer. So this is the priming site or a universal priming site, typically used for once you insert your DNA inside and you want to sequence it before you do other works, then you can use this T7 terminator primer. So the problem here now, once we produce our protein, if we don't do anything, you'll have additional amino acid because now you have 105 amino acid residues, which is 315 base pair long in genes in DNA, containing the TRX tag, right? And then you have his tag, and then you have S tag, all right? Now you have 3 tags on the N terminal, which is upstream of your DNA. And then you have his tag at the end, right? So let's look at TRX tag. Let's look at S tag, and let's look at his tag, right? So S tag is for Western blot, all right? So you can see whether your protein is expressed or not. You can detect it using the antibody for. And then for TRX tag is you can increase the solubility of your protein by having this tag. All right. But if you don't want this tag, you can use thrombin here. The thrombin is a protease. You can after you produce a protein, you add the enzyme. The enzyme will cut this side, and then it will remove the TRX tag and his tag leaving only the S tag, right? The problem is, let's say you want to produce protein without the S tag, then the solution is not to use PET32. That's why we go back to the PET vector series. Let's look at the option that we have, right? So we don't want his tag, we don't want S tag. So you can look for different types of PET. So not PET32, look at PET31, what does it have? Look at PET12, PET20, what does it have, right? So now let's, before we go further, let's take a look at his tag purification. So the problem when we produce protein is that we have a lot of proteins in the cell, and we just want to pick up the cell that the proteins that we want, which is the protein that we produce through the PET vector system just now, right? So to be able to do this quickly, or of course you can use a lot of chromatography method, separate your protein one step at a time. But to be able to do this rapidly, and this is very important because if you do it slowly, it will use a lot more time. You lose a lot of protein in the process, so that it's not very efficient. So you want to do this as efficient as possible. We use this his tag purification. So we can add polyhistidine, usually 6 residues of at the terminal, either terminal, N terminal, or the C terminal of your protein, right? So which terminal do you choose? It depends. You have to do some trial and error. Some proteins, you're producing enzymes. Some enzymes might not like it in the sticking at the N terminal because that might interfere with the activity of the enzyme. So we have to choose the C terminal instead. So we have to do some trial and error. That's why here it's important. His tag at the N terminal or the C terminal or somewhere internal, right, in the middle. So you can choose his tag. So what happens is that once the enzymes is being expressed, your protein is being expressed, and it's being translated, it becomes protein. It will fold primary, secondary structure, tertiary structure, quaternary structure, and it will have the his tag that you add, right? The polyhistidine tag. So this polyhistidine tag will form a chelation bond with cobalt or nickel, all right? And you can easily have this in the column, and this will bind very strongly to the cobalt or nickel, and other proteins won't have the ability to bind. Hence, using this method, you can separate your protein very quickly compared to the other non-targeted proteins. So inside the cell, E. coli cell, you have different types of proteins, and you have proteins with the his tag, right? With the his tag. This is the tag protein. So you can break the cell using sonification. You can freeze the cell and then thaw the cell repeatedly and break the cell. So there are different ways of breaking the cell. And then you can put it inside the column, and this column contains, it's just like a piece of filter, right? It contains cobalt or nickel, all right? I think nickel is more commonly used. And then you will wash it with buffer. The protein that doesn't have any his tag will go through the column very quickly, and it will wash out, right? Will wash out. After that, you have to add imidazole, which is a compound that is used to remove the chelation binding from the chelation binding between the protein and the nickel, because imidazole will also bind to nickel, but it has higher affinity compared to the his tag protein, so it will displace the his tag proteins, and then your protein will come out. All right. So this process is very quick, depending on your column. I think it's about less than half an hour. You can get almost very pure protein. Right. If you're worried, then you can do another round of purification using a different column, and then mostly it's usable already, right? So the steps in DNA cloning for expression, for example, or other purposes. First of all, you have to have DNA fragments, all right? Using RE or you're doing by PCR. You ligate it into the vector that you want to use. You transform into your E. coli, and then you do your selection, you confirm, and then you can look at expression as well. So for class activity, let's do this together. All right. Let's construct a PET vector using green fluorescence protein based on PET16. I just use PET16 over here because I have PET16 in the lab, right? So first of all, let's take a look at PET16's sequence or map, for example. All right, so this is PET16. You can Google it as well. You can find it. Let's inspect the features we have over here. So we have T7 promoter, we have lag operator, all right? That's where the lag I will bind. PET16 also have a lag I over here, all right? And then we have XBA site upstream of RBS, ribosomal binding site. We have the NCO site, we have the N-terminal histag, right? This is N-terminal because methionine is here, right? And then you have histag over here. And then you have NDE as your site for your cloning XH01 or BAM-H1. You just only have 3 choice of restriction enzymes to use. If your protein doesn't fit in, doesn't contain all these 3, it's a difficult cloning, right? And then you have factor XA. So this is also a site for cutting using protease. So after you express, you can cut it with protease here. If you cut using protease, you'll lose the histag. If you want to use the histag for purification, you do purification first and then remove it with protease, right? And cut it with protease. So this is our choice. So let's take a look at our gene, which is this one. Let's copy that and let's look at gene bank, all right? Some of you might get tired and boring with gene bank, but I've been using these throughout my career, so get used to it, right? So there's a lot of GFP protein that you can find. In fact, GFP protein is very famous, and it has been modified a lot by different people to enhance the fluorescence to make the signal much more stronger, right? This particular GFP is not the original GFP from the organism Korea victoria, which is is it the jellyfish? I think, right? It's not the original, but it's been modified. Usually they use the eGFP. They put the E in front, which means E is enhanced, right? It's an enhanced GFP. So, but nobody really cares so much for this particular case. It is yeast enhanced green fluorescent protein. Maybe they change some codons inside to make sure that they express better in yeast, right? But we'll use this gene. And this is the sequence you'll get over here. So you'll notice straight away that it doesn't start with ATG. So this is not the ATG. Maybe this is the ATG. And then this doesn't stop with TAG, TGA, or TAA. But there's a TAA over here, so maybe this is the stop codon. So to solve this problem easily, we just click here, the gene. The gene starts at 14 to 730. So it's specified over here, so it's quite correct. So 14, this is 10, this is 14. So I think this is ATG, right? Or you just can do this and click pasta, and then you'll get your ATG all the way to TAA. You can copy that one. All right. So typically, let's just put it in Notepad so that we don't lose it. That's our sequence, and then let's remove spaces and line breaks, right? Let's look for that tool. Let's use the second one. Let's copy this. All right, this is when the internet is making our life a bit difficult. All right, let's try. All right, so I use this and I think it worked quite well. Remove line breaks and process, and then you have everything so without line breaks, without spaces. So you can copy this. You know that you don't have line breaks when you adjust the window, and it's following that because of the line wrap. All right, so this is your EGFP gene, right? All right, next step is to confirm the RE sites that we're going to use, NDE, XO, SHO1 or BAMH1, because we want to put our gene inside here. All right, to do that, of course, we'll go back to our lecture and use our Takara bio, all right, or any site that you like, and copy your GFP gene there. I did mention NDE1, all right. All right. So we have XHO, X is here, XHO1, and was it BAMH1? Check that again, BAMH1, all right. And also BAMH1, A, B is here, all right. And submit, all right. So we have NDE1 cut once at the position 230. So that's our gene is about 700 just now. So 230 is about 1/3 of the way. So this is a problem, all right? This is a problem, but how big of a problem? All right. So we cannot use NDE1, all right? But we can use XHO1 and BAMH1, right? So we have another choice, right? We have another choice, which is to have NCO1 over here. But when we use NCO1, we cannot have his tag, right? We cannot have his tag. This is the N-terminal his tag, right? We will lose this N-terminal his tag because we'll be putting NCO1 and somewhere, for example, XHO1 or BAMH1, because these two sites are usable. Just to check whether we can use NCO1, right? NCO1, we click NCO1 here and we submit again and see. All right, this is another showstopper. No, it's a no for NCO1 because NCO1 twice, right? Twice at this location. So NCO1 is a no-go as well. All right, now we have a real problem, all right? So what would you do, all right? You can use XHO1 and BAMH1. You can put it in between, but you'll have additional this one. But you will have additional material also because of this, because our expression and translation will begin at this methionine site. So maybe it doesn't matter if you're not doing very strict cloning, right? Very precise cloning. You can do XHO1 and BAMH1, right? So the next step is, all right, so chosen RE sites will be XHO, XHO1 and BAMH1, all right? So let's take a look at SHO1. The site is a palindromic site, so you can see that it's a CTC GAG, right? CTG GAG, or you can easily look at XHO1. No, I'm typing wrong. One sequence, all right? So you can look at the NEB site, for example, or you can find from any site. That's the sequence CTCGAG, right? Let's take that sequence out and just put it here so we know GAG and what is BUM H1. BUM H1 sequence, and then you can get the GGATCC, right? GGATCC. GGATCC, right? There you go. So the idea is to include this site into the terminals of our gene so that we can cut it later and include it into our vector, so PAT16, right? So to do that, we will have to design a primer, right? Design a primer. Okay, so 15 base pair typically. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's just take there, Control C. So this will be our forward primer. Forward containing Excision 1. All right. So we just paste that, for example, and let's just put a gap so that you can see it clearly. Copy this and then include this, right? So by having this primer, right, of course, this will be 5 prime, this will be 3 prime. You can send this primer for to the primer synthesis company. They'll synthesize it for you, and then you'll have this primer. And this primer will work well with PCR because this will be the annealing part, right? It will function, it will bind to your DNA. This will be the extra. But from the second, from the reverse strand, from the second cycle onwards, this will be also amplified, right? You'll get this sequence added, right? So this is how we add sequences into our gene. We can add that sequence very easily using primer. So this is basically we're using PCR to synthesize extra bits. We are making our own linkers, not just using by ligation, but we are using primers to do that, all right? And then for reverse, for example, for reverse, we have BUM H1, all right? I always ask my students to do, just to put the RE name inside the primer so that they don't get lost. So we add it here. TAA 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You can do more than 15 if you want, but it's okay. Okay, and then at the end, we'll add BUM H1. BUM H1, right? Like that. Okay. So again, reverse primer, we have to reverse and complement, right? We have to reverse complement all the time. And we just add this and reverse complement this, right? Reverse complement DNA. I'll just use this one. Let's add that one, submit, and I get that one, right? Okay. So you can see, let's put back the hyphen so that we can see clearly. The interesting thing about restriction enzyme, because it's a palindromic structure, once you, even if you reverse complement it, it will still do the same, right? GGG, ATC, reverse complement is GGG, AT, so it's okay. But the sequence from there onwards will be different, right? Be different, right? So this will be your reverse primer, right? 5 prime, 3 prime. And you can order this. What happens is that the PCR product will include XOH01 here, will include BUM H1 here, And after PCR, you will add RE, and the RE will make a sticky end, right? Sticky end. And then you will do the same for your PET16. Your PET16 will produce the same sticky end, and you join this fragment to the linearized plasmid, and then you add ligase, then you join them together, right? So that is how we put our GFP gene inside our PET16, right? So let me just, all right. So this is our PET16. So now our GFP will enter nicely between XH1 and BAMH1, and then it will have a his tag at the end terminal. All right. And after growing it in E. coli for overnight, for example, if it's expressing, because it is a GFP protein, you can see the cell is greenish in color. You can put it under UV, it will glow. And that's what I did for the student experimentation a couple of years back. All right. Then we purify this protein using his tag column. All right. Another option, right? Let's because there's always alternative to cloning. For example, let's say, all right, let's say you want to have his tag at your C terminal, right? At the end of your protein, right? You want to add his tag over here, right? So let's inspect here. The his tag codon over here that is being used is CAT, 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 CAT. So if you count how many cats there are here, there's 1 cat, 2 cat, 3 cat, 4 cat, 5 cat, 6 cat, 7 cat, 8 cat, 9 cat, 10 cats. Oh, but the final one is a CAC, but CAC will also produce histidine, right? If you just look at the codon table, it will still produce histidine. So there's a lot of cats, right? A lot of cats, all right? So another way to include his tag at the end terminal, all right? So this is your stop codon, right? This is a stop codon, all right? Okay, so let's adding, sorry, oops, adding his tag at the C terminal, right? So to do that, all right, we just need to change the reverse primer. So what we want is, let's take some sequence over here, maybe a bit more. Let's work from here. All right, I just copy this. So this is our stop codon. To make sure that it translated to become histidine residue, so we have to put it before the stop codon, right? Before. So let's add the cats here. CAT, AT, CAT, AT. There's 4 cats already. 5 cats, 6 cats, right? Let's add 5. Normally I'll add CAC, but because this example over here is CAT, we can do CAT as well. So when you do this, you'll be producing this type of proteins, right? This type of protein. The end product will be this type of protein because now you have his tag at the end. So to be able to do this, to clone this, of course, you need to use BAMH1 again, right? At the end, so you add GGA, TTC at the end, and then now you copy BAMH1, you copy the stop codon, you copy the cats, right? And then from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Maybe you want to go a bit more, but let's try 15. Okay, copy, go to reverse complement again, my favorite side. All right, reverse complement, then you get your over here G, hold on, this is BAMH1, this is BAMH1. How come the site is not the same? All right, hold on, I have a problem. Oh no, I copied the thing wrong. It's supposed to be one extra C over here. My copy was wrong. You can see that you can, nope, GGA TCC. So GGA, there's two T's instead of this one. So let's just correct that again. Let's delete this one again. GGA TCC. All right. So guys, you can see here that even copying and pasting can be very dangerous. So make sure that you don't get that wrong. All right, then submit. Because in theory, you should get the same GGA TCC over here, and this one is GGA TTC over here, right? So delete this. Excuse me. Then we're done. All right, we have histidine tags in our gene at the C terminal. That's how you do it, all right? So you can see that modifying gene is very simple, especially at the terminal. Water. Okay, before I proceed, any questions? Because we'll be pushing this idea just a bit more. And I think I'm going a bit fast because this is something that I do most of the time in my research. So I get used to it. And I tend to go very fast here. Any question? No problem. All right, let's push the idea to a bit more extreme. For example, let's look at our PET16 here. Example, let's say we want to use XBA site, right? XBA site, and because let's say the other sites are not an option. We want to use an XBA site instead of the NDE site or XH01 or NT01. So we want to start from here. So what do we need to do? All right. How do we modify this? So to be able to use XBA site, first of all, let's check just in case if there's XBA site there. I think XBA site is not cutting here, so we can use XBA site. All right. So we check XBA site is clear. We can, it's not inside the gene. We can use XBA site. So from PET16, all right, if we use XBA site, we put our gene here, we will lose RBS, all right? We need this ribosomal binding site, right? We need this ribosomal binding site. So we'll lose this ribosomal. So we cannot lose that. Without the ribosomal binding site, we don't have good translation, and our protein would not be produced, right? So what's important is we need the promoter. We not necessarily need an operator, but we need the promoter. We need RBS, right? Or this ST sequence, another name for it. And then we need a stop codon, right? And then we need a start codon. And another thing is that the distance between RBS and the start codon is also important, maybe about 7, 8 to maybe 11, up to 11 base pair. So the distance is also important. If it's too far, then it's not good, right? So how can we work around when we want to use XBA1, right? Let's take let's say, using XBA1 site. And then we need to add RBS in our sequence. So let's take 15 base pair from our gene, GFP. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, let's copy that 15 there. And our XBA site is TCTAGA. Let's just write it there so then we don't get confused. And let's just copy and include this. So that is our, typically without RBS, that will be our outcome, right? TCTAGA with the complementary, not complementary, 15 base pair of our 5' gene, right? 5' end of our gene. So from here, let's add RBS. So where do we get our RBS? We just take this over here. Our RBS usually is a GA rich region, right? GA rich region. So just find the Lady Gagas that you have over here. Let's start from here. GAA, GG. We have GAAG. Let's put a hyphen there and GAA. Actually, you can copy directly from here. I think that's no problem. Yeah, just copy that. Let's start from G. It's okay. You don't have to be precise. All right. Okay. That's your RBS. All right. So I mentioned just now the distance from the RBS and the start codon is important. So once we copy from here, we just copy the same thing all the way up to the ATG of the original site. Then that includes our RBS, including the spacing all the way to the beginning of our start codon, right? To our start codon. So with this, just remove the spaces, remove the space over here, all right? And now we have 5' and at 3'. That's your primer, your forward primer for using XBA site, right? So I just showed you 3 different examples of how to clone the GFP protein. First, with the tag, if you want to use the tag, or you can use this. This is a forward primer, right? This is a forward primer. So this is a forward, or you can use the forward primer using XBA and adding his tag at the C terminal. Hence, you are eliminating the his tag at the N terminal and the extra, deleting the non-required, unwanted sequences that is originally available on the vector. So you can do that. Hence, there's a lot of flexibility if you know what you're doing. You can modify the vector as much as you want using the knowledge that you have of constructing the primer, right? So, of course, you have to check this part of the primer so that the TM value is okay. If the TM value is lower, you can increase the bases, increase the TM value, but you only calculate the TM value which is complementary to your gene, right? So that is what we learned previously. Check the TM value, but so some of you might have concerns about, doctor, this one is too long, right? It doesn't matter, right? It doesn't matter, right? It doesn't matter because you'll pay extra for the primer, but it gets the work done. It's no problem, right? So some companies will do this for you. In fact, you can find companies to do this cloning for you because somehow less and less laboratories are doing their own cloning these days. Maybe because they are working, mammalian cells or something like that. So they are not used to doing a lot of cloning, technical cloning like this. But I think at least for its 5 lectures that we've gone through so far, you see that it's no big deal. And then, in fact, if you can do this, if you continue to study in your master's or PhD, I think you can work in any field, regardless of if you're working with plants or humans or medical biotech. There's a lot of opportunity. There's for people who can clone, and then by knowing how to clone, you can set up different experiments, alter, modify different genes, putting different genes in different places. But our limitation now here, because we are depending on E. coli, and I can only teach you things with E. coli because that's what I do. And if you're working with yeast, maybe there's a different set of vectors, there's a different set of tools, but I think using yeast and also other different cells, there's also a lot of different tools as well. But E. coli is the simplest that you can get. If you get the basic idea here, I think you can do different types of cloning. So let's go back to our group activity, activity 5, right? Activity 5, which is producing spike glycoprotein for PET21D, all right? Now I'm specifying a different PET for you. So you can look at the PET vector 21D, or there's no link over here. So the link you have for PET16 here, you just, I think you can put PET21. You have to choose the A variant, and then you can get PET21. All right, so that's PET21. PET21 has more features compared to PET16 because I always choose the simplest example in the class, but it's not that complicated, right? So it uses ampicillin, it has lag I, but what's important is now you have more sites to choose from. So the sites that you can choose from, you have XBA, you have RBS there, you have T7 tag over here. So let's look at our lecture note again, what are T7s for. You can check that one out if you want to use. It's for detection, I think. So the D is over here. This is the PET21A, the B variant, the C and D. The D is different because you have an NCO site rather than an NDE site and NHE site over here. So that's the minor changes from the D version of this type vector. All right. And terminator over here. So our aim is to use the gene of pangolin coronavirus spike glycoprotein gene. This is the extension number. So I'm supposed to have like a background story. You found a dead pangolin, and then coronavirus was detected. Then let's clone and express and see whether it's dangerous or not. But I was working a bit late when I was working on this yesterday, so I didn't come up with a background story for that. But you get the idea, right? So this gene, I think, in the gene bank was registered, I think this year in year 2022. So it's quite a new gene, I think, a new, at least a new registered sequence. So identify the RE that you want to use, or which one do you want to use, and then determine what's your approach to clone the gene as a his-tag recombinant protein, right? So this time in the objective, I put the his-tag protein. I did not specify N-terminal his-tag or C-terminal his-tag. It's up to you. You can do that, right? So actually, I gave you a lot of ideas already. So by incorporating it in the primer, you can basically do anything you want, right? You can even add his-tag at the both terminal, right? Was it termini, right? Okay. And what else do we need to know? We have his-tag over here, right? For example, we have his-tag. So this could be your C terminal his-tag if you can use extension 1 or not 1. So so desirably, if you can use extension 1, it's better because it's closer. And also you can see for this particular example, the his-tag is not TAT, TAC. There's no cat over here. So I was quite excited when I see a lot of cat, but this TAC, it's more cat, like cat, not cat. All right. And I think everything else is self-explanatory, maybe, right? So just give it a go, all right? And as your last assignment, I think you did quite well so far, although I have not get enough opportunity to actually go through every single one of your reports, but more or less, I think the UPM students are doing a lot better from the SIT students, but the SIT students are second year students. So they have a lot more disadvantage, I guess. All right, so before I end this lecture and pass to Dr. Manraj, I guess, any questions? No question? All right. If no question, Dr. Manraj, do you want to say anything before we end?
Nothing much. Thank you very much, Dr. Azam. To all the students, this Friday, I'll be having a class and a session as well to really talk about how these designs of the recombinant proteins can be used for various purposes, especially in the vaccine formulation. And then we look at the toxicity of these testings of these newly formed vaccines. So I think that will be covered in my class this Friday. So to the SIT students, I believe you have class. It's going to be an online class. So therefore, I will share the Zoom link and also the recording so that you can have a look at it at your kind perusal and your time that you are available to look at it. So that's it from me. Thank you very much, Dr. Azam.
Okay, thank you very much. I will also upload my recording of this lecture afterwards once it's available. All right, thank you once again. I enjoyed having the class with my own students and also students from UPM. Hopefully, in the future, we have opportunities to collaborate again like this. All right, okay, thank you very much and see you again next time. And by the way, the assignments, the activities, the deadline is on Christmas Eve. I put it on 24th of December because last day for SIT 24th, right? Right. Okay. I think it's not much difficult compared to previous assignment, so please have a go. Right. Thank you very much, and see you again next time.
Recording stopped.